introduce myself. My name is David Park. I'm the director of the University of Ottawa Brain and Mind Research Institute, and I'd like to welcome all of you to our second annual Brain Health Awareness Week, presented by the U of B MRI in conjunction with the City of Ottawa. So this has been an amazing week, filled with incredible science and interactions with you and the community, related to the priorities of what we do in the brain and mind. For example, stroke, Parkinson's, depression, neuromuscular disease. And we're going to end this week. Yes, exactly. With what's going to be a really interesting and exciting debate on stem cells. And actually, we do this every year. We're going to continue to do this every year because I think there's some incredible topics that we need to kind of explore in a more in-depth way. So last year we had a debate on depressants, antidepressants. Were they actually effective or were they prescribed? And I think this year on stem cells is a timely topic given all the advances and media and attention given to stem cells. So before I do this, I just want to mention that this week is very special to us because it's an opportunity to engage with you in the community and highlight some of the exciting things that are going on. Now, on a second note, it's very exciting for me because this will be the last day this week that I have to wear a suit. In fact, I think I'm running out of clean suits. So let me tell you a little bit about the brain and mind. Some of you have heard it already, but it's important to get it out there, this message that it's important because it was set up to really coordinate the amazing brain and mind related research that's going on in the Ottawa area. So let me just give you a scope of what's happening. 5 major academic hospitals, ranging from GEO, Royal, TOH, all of those that you're familiar with. 6 different faculties within the University of Ottawa, and also Carleton University. And so we have more than 200 really incredible multidisciplinary researchers, some of them are here, who are banding together to tackle some of the really intractable problems of brain disorders. And in the brain and mind, right now we're focusing on a few things with minds to others, but the focus on stroke, Parkinson's, depression and suicide, neuromuscular disease, just to name a few. And throughout all this, to really, I think, a timely introduction to this today's topic, that's to understand what's going on with the brain, what's going on with the brain circuitry, because that's the ultimate arbiter of how you guys and we behave. So today is almost the last day, but I just do want to mention briefly tomorrow is our yoga event. So at Tabaret, which is right across here, it will be sunny. Please come join us for our first ever Yoga and You fundraising event. It should be fun, there's going to be food, you're going to do yoga, and you're going to learn a little bit in a much more relaxed atmosphere about what's going on in your brain. Okay, so on with the show. We as humans have 100 billion brain cells. Actually, it's a little bit lower. I think the recent estimate is 84 billion. And 100 trillion connections. And all of these things determine how we act, how we behave, how we think, how we remember. And this is quite phenomenal. So what's really exciting in the past few years has been at least 2 things. Okay, so number one, these 100 trillion connections with 84 billion neurons are not static. So we are not like computer chips. Right? In fact, we are now, in our brains, always changing in a way that promotes and highlights our ability to be plastic. Most of you have heard the word neuroplasticity. So that's number one. Number two, we of course now know that the brain has this ability to actually spit out new brain cells with neural versions of stem cells. So those two things are quite amazing because now you can use your imagination to figure out maybe we can use those processes to do a whole lot of different things for a whole lot of diseases and maybe even prevent us from all getting too old. So is it really ready for prime time? And that's going to be the discussion we're going on today. And we have some amazing panelists that I'll let Adrian introduce. They are amazing, but I do want to put a little bit of a preemptive thing on them. And that is, these amazing scientists are amazing. They're incredibly knowledgeable, incredibly balanced, but I have told them specifically to go at it. Perhaps don't come to fisticuffs, and that's why we kind of separated them, big aisle in the middle. But if you do, someone get a video of them, because it'd be a great YouTube video. Okay, so I want, in my distinct pleasure, to introduce Adrian Harwood. Adrian has been so generous to always moderate our debates. Adrian is the anchor, of course, of the CBC News Ottawa at 5:30, I think it's 6 now, and also CBS News, CBC, sorry, News Late Night at 11. Tell you a little bit about Adrian. He is an Ottawa native. He studied political theory and history at McGill. And he did things other than television, so he was the host of the #1 rated All in a Day on CBC Radio 1 in Ottawa. He's been guest on a number of national CBC programs, including As It Happens, Sounds Like Canada, and The Current. And of course, he's incredibly immersed in our community, spends hundreds of hours every year at events in Ottawa and the surrounding area, and of course, this is an example of that. Adrian, thank you so much for taking the time to do this. Adrian.
Thank you very much, Dr. Park. Can you hear me back there? No, you can't hear me. Okay. I should know how to use this. Okay, is that better? Okay. Can you hear me now? Hear me at the back? Okay. Well, good evening. Welcome, everyone. Thank you for joining us this evening at the University of Ottawa's Brain and Mind Research Institute Brain Health Awareness Week event, this stem cell debate that we're having tonight. It's so great to see so many people here on an evening where you could be at the City Folk Festival. You know, you could be doing a lot of other things, so it's wonderful to see all of you here. It's always a delight for me to be back here at the University of Ottawa because I'm really a child of this university. My dad worked here for over 35 years. He was a professor here and also worked as an academic advisor. My mom was a lecturer here. Two of my 4 sisters attended the University of Ottawa, one in the law school and another was in criminology. I wasn't smart enough to get into Ottawa U. I went to another university in Montreal. I always wanted to be a GG, so I feel like an honorary GG tonight, so it's really a delight for me to be here once again. Now, as David mentioned, last year's topic was about whether antidepressants were overprescribed. And tonight's topic shifts to another therapeutic avenue that is being investigated, and that is the topic, are stem cells ready for regenerative therapy? Now, stem cells really came to the fore of public consciousness in the 1990s. They seem to have the potential to assist the body in fighting against diseases of degeneration like Alzheimer's, and even to help to grow new parts to treat conditions like spinal cord injuries. Billions of dollars have been invested by governments and private institutions to conduct research into how best to use stem cells, what types to use, and how to deliver them to the body. Monies have also been invested to fund thousands of clinical trials to treat patients with an array of conditions from heart disease to Parkinson's, blindness, and blood cancers. And as we know, Canada has been at the forefront. It's been at the forefront of stem cell research. And while there is great hope and belief in the technology, some have argued that the enthusiasm for stem cell technology outstrips the science. Tonight, we hope to engage in the debate about whether stem cells are ready for regenerative therapy. And we've assembled a stellar group of experts to address the question and to engage you, our audience. And as David suggested, tonight is going to be a battle royale. Now, our first panelist is Dr. William Stanford. Dr. William Stanford is a senior scientist at the Sprott Center for Stem Cell Research at the Ottawa Hospital Research Institute. He is a full professor in the Department of Cellular and Molecular Medicine at the University of Ottawa, and he is a Tier 1 Canada Research Chair in Integrative Stem Cell Biology. And he is going to be making the argument for regenerative therapy. Now, just before I get to Dr. Stanford, I wanted to ask the audience, I want to get a sense as to where you are at. So a show of hands, who believes that stem cells are ready for regenerative therapy? Can you just raise your hand if you believe they are? Okay. It's shocking that these folks agree with that proposition. And who believes that they are not ready? Dr. Malin? Okay. Okay. So we're going to begin with Dr. Stanford. Dr. Stanford, you have the floor.
Thank you so much. So I just first have to apologize to everyone because I apologize to our organizers and everyone here because this really isn't a debate. In fact, my colleague and I are going to tell you that stem cells are already in the clinic, that they're already in clinical trials, and they've already saved lives. So this isn't so much a debate about the future, but an opportunity for us to explain really what's going on with stem cells. So first, let me give you the Cliff Notes version of stem cell biology. And we have a couple of different types of stem cells that are relevant to the brain. The first one are the neural stem cells. And of course, it's kind of hard to get the neural stem cells out of an adult. And so the first set of clinical trials that have been performed with stem cells, with neural stem cells, were actually isolated from fetal, from the fetus. So these are from aborted fetuses. And so that's a bit of an ethical debate. We're really not going to talk about that today, but I will talk about it from the standpoint that those studies really form the foundation of the new and better types of stem cells. So what are the other types of stem cells? Well, there's pluripotent stem cells, and what pluripotent means is it means that a cell can become every single cell of the human body. So it can become that fetus, it can become the adult. So there are two flavors of these pluripotent stem cells. The first is the embryonic stem cell, and that would have been derived from pre-implantation embryos. So essentially, and all of them were derived from extra embryos following in vitro fertilization. So that the embryos would have gone into the trash can, or they would have been donated to science. And so in some of these cases, they were donated to science, and cell lines were generated from them. The second type of pluripotent stem cell is called an induced pluripotent stem cell. Now that stem cell is actually to be derived from any cell of your body, essentially, so the skin is often used. And that can become any cell of your body, essentially. So a reprogramming event, which garnered Shinya Yamanaka of Kyoto University in Japan the Nobel Prize in 2012. And just to mention also that how important embryonic stem cells are, that was essentially the 2007 Nobel Prize. So the other thing I need to talk about, and just as a refresher, is what are we talking about when we're talking about a clinical trial? What are some of the important issues? So first, safety. So we want to make sure that these cells are safe when transplanted. we must have the right cell population. We want to put cells that have the capacity to make neurons into the brain. Rejection, we're worried about rejection. Now, everyone knows here about kidney or bone marrow transplants and the possibility of rejection, so immune suppressants are used. Or if they come from the same cell, from the same individual, like in the induced pluripotent stem cells, then you don't really have to worry about rejection or immunosuppressants. And finally, where are you going to put the cells? Can you put them back to essentially where they came from, where they need to go? So where in the brain? Now, so the day after Bill Clinton was elected president in the United States, this professor at Harvard, Isaacson, he put in the ethical paperwork to ask to take fetal neurons, fetal brain tissue, and inject it into Parkinsonian patients. And this didn't work for everyone, but for those patients that worked for, patients who were essentially couldn't walk or do anything, they were out playing tennis afterwards. So for certain patients, this worked beautifully. And so this, now recently, last year, there was just a report of the patients who have passed away since then, and those patients, it was found that those patients still, those transplanted cells did what they were supposed to. They were still making dopamine. So one good news about this ethical dilemma, though, is one embryo of 6 patients. So that's where we are there. But that gave us a lot of information. Moving forward, children are born with lysosomal diseases and other diseases where they're going to die shortly after birth. And several clinical trials have been performed using the same source of cells, the fetal and brain tissue, transplanted in these patients, and a number of the patients are still alive when they should have been dead from years ago. So again, here we have a situation where we've demonstrated that it's safe. We've demonstrated that these patients also have gone off immune suppressants. So after 1 year, they went off of immune suppressants. But for at least 4 years, they've still had these working cells in their brains. So ALS, everyone knows about Lou Gehrig's disease. There's also been 12 patients who've been treated with fetal tissue for Lou Gehrig's disease. All 12 of those patients at 18 months of age, at 18 months post-transplant, have all shown that they've not progressed in this disease. So all these studies basically told us that if we have the right cell population and we put them in the right place, then they can work. They can integrate into the brains, all those, make all those types of connections that Dr. Park just talked about. And so moving forward, now we're on to pluripotent stem cells. Now, we don't have any pluripotent stem cell transplants yet into the brain, but we do have transplants. There are 8 clinical trials that are currently enrolling patients to cure blindness with cells that make up the retina. And so 3 of those clinical trials have started to report results. One of the clinical trials has already started to report results, and those have been very good. So patients who are blind are now able to see fingers and count fingers in front of them. Finally, in Japan, where induced pluripotent stem cells were developed just in 2007, there's already a clinical trial essentially doing this there. So the first reports are, again, they're safe. So all of these studies have shown that they're safe and they're showing effectiveness.
Well, thank you very much, Dr. Stanford. I think you made a very strong case. And right now we're going to get a counter-argument, and we're going to get it from Dr. Judy Illes. Dr. Illes is a professor of neurology and Canada Research Chair in Neuroethics at the University of British Columbia. She is the director of the National Core for Neuroethics at UBC. and she's in the faculty in the Center for Brain Health at UBC as well. She holds affiliate appointments in the School of Population and Public Health and the School of Journalism at UBC, and the Department of Computer Science, is that better? Computer Science and Engineering at the University of Washington in Seattle. She's also a life member of Clare Hall at Cambridge University, and she's going to be arguing against the proposition that stem cells are ready for regenerative therapy. Dr. Illes.
Thank you very much, Mr. Harewood, and thank you all for joining us here tonight. I am indeed going to argue that stem cells are not ready for regenerative therapy for the brain, and with all due respect to my esteemed colleagues, Dr. Stanford and Dr. Vanderpoy, since we are here at the University of Ottawa Brain and Mind Research Institute, our focus is on regenerative therapy for the brain. And I would submit that you can make a big soup out of just about everything that when you put into it, and you put everything into the pot, you will get a soup, but is that actually meaningful for the health care of Canadians with brain diseases? And so I'd like to base my reply on an opinion editorial that Professor Fabio Rossi and I wrote in February 2015 in response to a great deal of media coverage that our beloved NHL hockey player Gordie Howe received after he himself suffered a stroke and went to Mexico for some therapy. So this is an adaptation of that op-ed. The Canadian public is lucky that Gordie Howe, one of our national sports heroes, and his family are openly sharing the struggles and stories of improvement after a stroke he suffered in late October 2014. I can tell you these stories continue in the National Post and the Montreal Gazette. The latest I found was from August 15, in which there was a report from the Post, a human interest story, that Mr. Howe is now up to 200 pounds. He regularly goes to rehab. He is speaking somewhat, although not loudly, but there's little doubt that his spirits are high. His eyes twinkle and he smiles every now and then as he flirts with two young women, putting him through his paces at rehab. He even planted an innocent light kiss on the cheek of his occupational therapist and twirled her once as if they were dancing. The question at hand is he twirling his occupational therapist now because of the stem cell therapy he received in Mexico? So let's explore that. There are few among us who don't know someone with a brain disorder or a disorder of the spinal cord, suddenly acquired or slow-moving, that has affected a person's ability to move, speak, make decisions, and sometimes even cause deep personality changes. The openness of celebrities like Mr. Howe binds our community together in solidarity and empathy, brings national attention to the acute and long-term needs of people affected by brain injuries, and reminds us that our healthcare and research systems strive and are at the same time continuously challenged to advance care and cures. Taxing personal and societal resources for brain injury is the emotional and financial investment in untested treatments sold abroad, from which direct positive results are in the best case unlikely, and which in the worst case can cause harm to those receiving them. Recent reports of the Howe family's trip to Mexico in hopes of regaining some of the physical and cognitive functions that Mr. Howe lost to his stroke is yet another example in a long and seemingly unstoppable list of Canadians placing their hope in stem cell therapies for brain recovery in foreign companies. I'd like to help get things straight together with my colleague Dr. Mailer. At least therapy for the brain, which is our focus here tonight. Since their discovery in the 1960s, significant progress has been made in characterizing the properties of stem cells and identifying potential clinical applications for them. Stem cell interventions are routinely performed for a number of blood diseases, ranging from leukemia, congenital immunodeficiencies such as the anemias. They've been proven to work in some patients who suffer extensive burns, and they can even return sight to patients with damaged corneas after years of blindness. Here in Canada, stem cell-based therapies are being explored with very encouraging results for multiple sclerosis in particular. These clinical trials are in phase 1 at present. Those are safety trials. Those are not efficacy trials. Yet the data are promising. In laboratory, stem cell interventions are showing promise for a much wider range of afflictions, including spinal cord injury, Parkinson's, diabetes, and many others. Clinical trials assessing both safety and efficacy of various stem cell therapies are ongoing, with over 4,000 reported trials at the National Institutes of Health run website, and you can go to it yourself, clinicaltrials.gov. Repeat after me, clinicaltrials.gov. Okay, that is a good resource of information for you to understand what's going on in clinical trials for stem cells and other forms of therapeutics as well. To date, however, there is no evidence for effective stem cell interventions for a stroke, the kind of brain disorder that affected Mr. Howe. A stroke is a sudden loss of brain function caused either by disruption in the flow of blood to the brain or a rupture of blood vessels in the brain. The loss of function that follows it is due to the damage to the areas near the stroke and to the connections between those areas. Such damage may be permanent, usually to the loss of irreplaceable brain cells, or may be temporary. Time may certainly bring some functions back when those cells are stunned, but not lost neurons recover, or more often, when another brain area takes over for a damaged one. Despite much active research, though, there are no miracle cures, no miracle cells of any sort today that can be injected to either accelerate these processes in the brain or create cellular brain bridges where they would otherwise not occur. Companies who are selling these products are preying on desperate and vulnerable people and exploiting their hope, much like snake oil salesmen have done throughout the history of time. In this latest case of what we can call medical tourism, Gordie Howe's fame has surely flamed the commercial gain for the American company operating south of its border that sought him out. This case represents, in my opinion, an example of an individual family struck by tragedy and, I believe, tragically seduced by false promise. The therapy, in quotation marks, that Mr. Howe received would cost regular people, like you and me, not beloved hockey players, upwards of $30,000 for a single intervention. Mr. Howe received it for free. Besides this fundamental ethical issue, or neuroethical issue in fact, if Canadians have the erroneous impression that these therapies are easily accessible abroad, we will be unlikely to advocate for and support legitimate development and implementation of these trials in Canada. I, together with Dr. Mailer, and I'm sure our opponents, in fact, urge Canadians to speak with their physicians, to access reliable sources of information about stem cells, such as those published by professional societies, and to turn to that website that you all now have ingrained in your memory for good information. Reach out to researchers and scholars at local medical centers across Canada for advice and consultation. I reach out to the Howe family to support us, to support other Canadians affected by neurologic disorders, to pursue excellent care, and that our health system can really provide, and to resist the kinds of human interest stories that promote hype and ill-informed hope around certain applications of stem cell therapeutics. Help us to continue to make discoveries and advance the new knowledge we gain every day, so the next time that we all meet together, Dr. Mailer and I will join our colleagues on that side of the table. Help us to promote informed and educated choices by all Canadians that bring real brain health and well-being through prevention and ready for rollout science-based intervention. This isn't a message of pessimism by any means. It's a message of optimism and realism. We will be ready for regenerative medicine for brain diseases. We're just not ready yet. Thank you.
Okay, thank you very much, Dr. Ellis. I think the battle is on. I think in hockey terms, you are the proverbial instigator. And I think if Gordie Howe were here, he'd be proud of you, because I think you just threw a bit of a Gordie Howe elbow at your opponents by referring to them as being akin to snake oil salesmen. So we're going to have to follow that up. Dr. Derek Vanderkooy is a professor in the Department of Molecular Genetics at the University of Toronto. His lab is the Neurobiology Research Group. Dr. Vanderkooy is both the founding and planning committee member of the Ontario Stem Cell Initiative, the head of the Pancreas Program for Regenerative Medicine at the McEwen Centre for Regenerative Medicine, and he serves on the Project Management Committee for the Ontario Consortium for Regeneration Inducing Therapeutics. With his lab, Dr. Vanderkooy produced the first report of stem cells in the adult mammalian eye, published in 2000 in Science. Please welcome Dr. Derek Vanderkooy.
Thanks very much. Let me start by conceding Judy's argument. There are crooks and charlatans in stem cell biology just like there are in every other field. That doesn't mean just because there are a couple of dirty players during a hockey game that Gordie Howe and Wayne Gretzky should leave the ice. Serious hockey players, serious scientists should continue to do the kind of work that will lead to regenerative therapies for the brain in the near future. There are, I admit, charlatans and cheats and liars out there trying to take advantage of patients who are desperate for treatment. Almost all of these treatments, as Judy mentioned, are taking place in poorer countries. Even if they're originated from the United States or Canada, they're taking place in poorer countries. And the reason why that happens is that there is not sufficient oversights in countries that don't have enough money to spend it on legislation and on supervision of clinics. And so, the treatment that Gordie Howe received, there's no evidence was provided by the team that provided that treatment for a clinical trial. They've never run a clinical trial, a randomized clinical trial, where they can test to see whether these treatments work. There's no identification of what cell types they used. We don't even know they were stem cells. There's no evidence of efficacy in any of their treatments. These are the minimum requirements that you need to meet in richer countries that have oversight and that do have and call for clinical trials in order that stem cell therapies can be proven before they're offered to the public. And so there are bad people out there taking advantage of patients who are desperate. But there are also some very hard-nosed scientists running clinical trials in Canada, in Europe, in Japan, in the United States of stem cell therapies for the brain that are showing promise. And I think I can just paraphrase Judy by saying that, in a couple of years they're going to be over in this table. She already admits that it's just a matter of time until some of these therapies are legitimately characterized, have gone through clinical trials, have proven to be effective, and have a basic biological knowledge of how they work. And those criteria, I think, are critical before anyone should take one of those clinical trials, take one of those treatments. Without that sort of hard-nosed evidence, there's no reason to try an unproven therapy. Now, the serious scientists have taken this problem on. And so, besides the government agency that Judy identified, the International Society for Stem Cell Research, which is the biggest collection of stem cell biologists, has taken an initiative in trying to discredit some of these third world, poor country treatments that are offered by charlatans. And if you go to their website, the International Society for Stem Cell Research, they've identified some of these companies. They give patients questions that they should ask their doctors when they think about trying one of these unproven therapies in a country, a poor country. And they've tried to challenge some of these countries. In fact, they've been sued because of this problem by some of these companies. So I think there is a real hope. And I think that stem cell therapy, maybe we haven't pointed out the real advantage of it. Most of the treatments that are available now for stroke or Alzheimer's disease or many other types of disorders are not cures. What they are is they're slowing the degeneration down. People still get sicker and sicker and sicker, but their progress is slowed down. The progress of getting sicker is slowed down. What stem cell biology offers, though, is a chance for cures. Once you've lost cells, once cells have died in the brain because of a disease like Alzheimer's disease, the only way to replace those cells is through stem cell biology. If you've lost neurons, then you need stem cell biology in order to make those new neurons that can replace the cells that are lost. Now, I think that our opponents are going to argue that the brain's too complicated. It's, 100 billion neurons and trillions of connections. It's too hard to imagine new neurons coming into the adult brain and connecting correctly. This just isn't true. It happens normally in our brains. There are cells in the hippocampus of the brain, the area that's often hit first by Alzheimer's, and that is the site of memory storage, the short-term memory storage. There are new neurons made continually in that brain region. The new neurons are made, they become postmitotic. They divide, they become postmitotic, they migrate to the correct place, they grow axons, they make synapses, and they integrate normally into the adult brain. This is something that happens all the time. Now, there are lots of reasons why that process breaks down in Alzheimer's, but the chance of reinstating that process where we make new neurons in the brain that can integrate correctly is the real hope of stem cell biology. I'd like just to end by talking about three just early clinical trials that are happening in Canada right now for brain diseases. The first one is one run out of Freedom Miller's Lab, Hospital for Sick Children. They found a drug that allows new neurons that are born normally in the brain to survive and integrate better. And so what they're doing now is taking kids who have had pediatric brain tumors and had a radiation to try and kill off those brain tumors. The problem with the radiation is it also causes cognitive deficits. And what they're trying right now, based on animal studies that worked very well, is to give a drug that allows the new neurons that are left to survive better and integrate better in these children who have had pediatric brain tumors. So this is perhaps one of the most controversial uses of stem cells, not only in humans, but in children and in their brain. And yet, these are the kids who need these treatments the most because they have cognitive deficits that are a byproduct of their treatments for the brain tumors. And so there's a clinical trial going on right now in those children that have had irradiation to get rid of their brain tumors to see if they can improve their cognitive function by integrating new neurons into the hippocampus. There's great evidence in animal and human studies that new neurons in the hippocampus are a great help to memory.
Dr. McAvoy, thank you very much. Thank you very much for that opening statement. And I think in imploring your opponents to stay on the proverbial ice, I think you were channeling Don Cherry there in terms of getting them to stay and fight on the ice. I think we've almost exhausted our hockey analogies for the evening. Not quite. Our next panelist is Dr. Leonard Naylor. Dr. Naylor is a distinguished professor in the Department of Cellular and Molecular Medicine here at the University of Ottawa. He's also the co-director of the University of Ottawa Center for Neurodynamics. Please welcome Dr. Leonard Naylor.
Thank you. First thing I'm going to do is to actually help my opponents, but for a selfish reason. There are some very intriguing experiments ongoing that suggest that stem cells can be used to cure deafness. So that's a great help. But why does that work? And in fact, why do those neurogenesis in the hippocampus, why does that work? To cure deafness, you have to replace the dead cells, the cells that have died, that are sensitive to sound. They can be killed by drugs, such as antibiotics. They can be killed by trauma. They can be killed by listening to 110 decibel rock and roll music. Whatever the cause, when they're dead, you're deaf. These cells are called hair cells, and they don't normally regenerate. People have tried, got some intriguing preliminary results, suggest that you can induce new formation of new hair cells in the cochlea. But hair cells are fairly simple. Not only that, the connections they make to go from the ear to the brain are very simple. What do I mean by simple? I can explain this to my fourth year undergraduate neurobiology students in about 20 minutes. Now, let's go back to something Dr. Gillis talked about. Really, one of the holy grails of using stem cells for treating neurological diseases, the disease is stroke. The death of cells in the brain because of lack of blood supply and oxygen. Very typically, it's the cells in the outer rind of the brain, a structure called the cortex. Damage to one part of the cortex will prevent you from speaking, part roughly over here. Nearby, damage to that other region will prevent you from understanding speech. And every other advanced faculty of humans will be controlled by one part of the cortex or another. The cortex is not simple. In fact, we don't even know the number of different cell types in the cortex. Estimates 40 to 50 to 60 types. The connections are incredibly intricate. I don't even try to explain this to my advanced graduate course. In fact, I can't. Nobody understands the connectivity. The connectivity doesn't come from nowhere. It starts in utero with the fetus. It continues in a baby. As that baby is learning to babble and speak and recognize its parents, you're seeing neurogenesis and the formation of new connections in action. Now imagine a building under construction. There's a scaffold all around it. There are directions. Plumber, put the plumbing over here, connecting hot water to this tap and cold water to this tap. The electrician has to run the wiring in a very specific manner. How about the ductwork for heating and cooling? That is the case in the developing brain. There's scaffolding in the cortex. There are directional signals that say, you neuron type, form over here, and then migrate here. And then make connections with another dozen neurons of different types. What happens to a building when it's complete? The drywall is in, the garden's planted, well, the scaffolding is taken away. The instructions to the plumbers, electricians, ductwork people is gone. If a little part of it burns and the homeowner decides, where does this wire go? Chances are he'll electrocute himself and not restore lighting in some part of the building. That is the situation in the adult cortex. So, if you now take stem cells, neural stem cells of any sort, and implant them in the stroke region, you have to imagine that they will find, well, first of all, that they'll know what type of cell to become. There's dozens, perhaps as many as 60 different cell types. There's a recent conference in Spain, and they couldn't even come to an agreement. Many cell types. As you might imagine, the exact mix is different in the region that controls speech production and speech understanding. You not only have to have the right cells, they have to be different for every little region. There are thousands of these regions of the brain for every faculty you can imagine. If they do manage to form in the speech production area, they have to get input from the speech understanding area. They have to run wiring over centimeters in the human brain, many centimeters. And again, the guideposts, the instructions for the nutrition are no longer there. They were removed after brain development was complete. So now these poor, newly born cells don't know what to become, and they don't know where to go, and they don't know who to partner with. So, just like Dr. Gillis, it's not a pessimistic message. I think we can make progress in curing blindness, deafness, and eventually Parkinson's, because those are simple cases. With that under our collective belts, we can move on to the holy grail of a really tough problem, replacing the cells in our cortex with very carefully engineered stem cells, engineered for every precise region, and able to become the right kind of cell, make the right connections without the signposts. In fact, we have to learn about the scaffolding of the signposts more than anything else. I am not pessimistic. I think I'm realistic. I think this will take decades of research. And I don't think we should be making promises to Gordie Howe that some mix of cells is going to do anything at all for him.
Okay.
Thank you.
Well, thank you for that. Thank you for that opening statement, Dr. Miller. We're now going to enter the freestyle segment of the evening. And so I'm going to be posing some questions. We're also going to invite some questions from the audience. And I'm going to begin with this question to Dr. Illes. Dr. Illes, do you suffer from a lack of ambition?
I suffer from a lack
Yes.
of ambition. I
Yes,
have not
because your argument suggests that maybe you suffer from a lack of ambition in leaving the ice so quickly, when we all understand that you know, to coin the old Frederick Douglass phrase, no struggle, no progress. You have to stay on the ice, do you not?
So I would argue the contrary. I'm all over the ice with the very best hockey stick, but I want to make sure that the puck that I get to hit is actually round, not full of pegs and dust and things that won't make it slide properly, so I can make my goal.
So what's your main concern with Dr. Vanderkooy's argument?
So Dr. Vanderkooy, Derek, since it seemed to be Judy this evening in this debate, not sure how that happened. Talk about that afterwards. I heard Dr. Vanderkooy talk about clinical trials. I did not hear him talk about regenerative therapy for the brain.
Dr. Vanderkooy?
I guess those clinical trials are regenerative therapies of the brain, a chance to give a drug that will cause new neurons to be activated, born, and integrated into a circuit. There are other examples I can give as well. Spinal cord, there's a spinal cord trial going on now in Michael Failing's lab at the Western Hospital in Toronto, where they're putting stem cell-derived oligodendrocytes, usually the myelin-producing cells, into the spinal cords of patients. They've shown in animal models that these can remyelinate axons and actually improve function in animals. They're now trying a clinical trial under very specific conditions that I think are very hopeful.
So if I may respond, clinical, so I'm an ethicist, I'm a neuroscientist turned ethicist. As far as I know, clinical trial is research. It's not clinical practice. It's not reimbursable, not clinical practice at this time. And we have to be very careful when we enroll individuals in these trials for them not to have a therapeutic misconception of benefit that may not exist, because it still falls squarely in the domain of research.
Absolutely, but it's research that's based on careful, replicated animal studies that suggest we should move to clinical trials in humans. And this is the way it happens in every field. You do basic research on animal models. When you have enough success, you see if they translate into humans in clinical trials. That's the way that new treatments originate, and that's exactly what's starting to happen now in neuroscience of regenerative medicine.
Dr. Stanford, I think Dr. Willis is suggesting that you kind of, you work in the business of deception. Is that the case?
Well, you know, I would say I'm optimistic, but I would also...
Overly optimistic, perhaps?
Well, no, I again will champion what Dr. Ellis said about stem cell tourism and how detrimental this is. In fact, I think everyone, all of us as part of the panel have gotten phone calls or emails from desperate people asking about whether or not they should get the stem cell treatment. And we always talk to them, explain, point out clinicaltrials.gov, all of this, because it truly is snake oil salesmen and snake oil saleswomen. I will say, because I was recently called a bad name simply because I forgot to include snake oil women, saleswomen. So I must point out that. But I also, again, to Dr. Van Gooy's comment about clinical trials right now, so we can see the progression for Parkinson's. We took neural stem cells from fetuses, showed proof of principle. Now, very recently, just this year, it was reported that into non-human primates, so types of monkeys, that they created Parkinson's disease in these monkeys, and then they treated them with induced pluripotent stem cell derived neural stem cells. And again, this is experimentation. They took 3 different types of protocols in which to make these very specific progenitors for the dopamine neurons, and then they tried them in their monkeys, and they found that one actually really worked. It provided a profound benefit to the monkey, and the others two simply did not work. This is this process of research that we go through. So now we know it's safe. Now we know we have a protocol in which that works. Now we can do additional animal trials and then move into phase 1, phase 2 clinical trials for Parkinson's. And while I will concede to Dr. Mailer that is a baby step forward in terms of how difficult it is, because we're talking about essentially one type of neuron. But it's still, a few years ago, they said those cells cannot integrate into the brain properly. And the pessimists were wrong. We now know that they do integrate properly.
Dr. Ellis wants to rebut the argument.
I feel like I have to jump in here and just say that even though Dr. Stanford and Dr. Van Gooy are wrong about their estimation for readiness of stem cells for brain therapy, these are some of our top stem cell scientists in our country, and we're not talking about snake oil salesmen selling some weird product in foreign countries.
I was just taking poetic license. You
can't cross that line.
I was trying to be provocative. Did you want to continue?
No, I just wanted to be sure that we were not confusing.
No, I think we all understand this is the case. And so please, Dr. Miller.
I want to go back to the analogy that Len used about electric wiring of the house. So I think that what you were suggesting is that when some of the wiring breaks down in the house, we should burn the house down and move to a mud hut. That's not what we do. We call the electrician up, and he comes in and he rewires it. I think that analogy holds perfectly for the brain. We want to call in stem cell biologists. And it may be difficult. They may have to spend a couple of days doing the rewiring, but we want to call in stem cell biologists to come in and rebuild the connections in the brain. We don't want to burn the house down, throw the person out. We want to try and fix them.
Although in fairness, I don't think Dr. Miller suggested burning the house down. I think what he suggested was that he believes that there is hope in terms of dealing with blindness, I think you mentioned, also with deafness, and you also mentioned Parkinson's. But why not more? Why not other ailments or diseases or conditions? Is it because the brain is too complicated? Is that what you're suggesting?
To raise this point, the cells involved that die in Parkinson's is one type of cell. The wiring is not that complicated. When we go to the cortex, responsible for speech production, speech understanding, the order of complexity jumps many levels. It's vastly more complex. The wiring is vastly more complex. And the guideline, the directives to the electrician, wire this point to that, they're all gone. Those exist during early development. There's many scaffolding cells, some are called radial glia, for example, that are there to guide early development. You don't need them in the adult, they're gone. I agree with Derek. We have to continue. It's just we're not looking at 1 year or 2 years or 10 years. I think we're looking at decades of research before we understand how the early wiring happens, so we can try to re-induce it in a damaged brain. I think it's a matter of degree, not don't do this, don't burn the house down, just don't expect the electrician. He's got lots of other jobs to do. He's got no way to avoid a few decades before he comes.
Let me just give one example of that argument that the cues for telling neurons to integrate and grow correct axons are gone in the adult. There was a wonderful paper published quite a few years ago by Jeff Macklis's lab at Harvard, where they showed that in an adult rat, where you would say all the information is for building the brain is gone, you could get new layer 5 cortical cells to be born in the adult brain and send an axon all the way from the brain, all the way down to the spinal cord, and make the correct connection in the spinal cord in an adult brain. And I thought that was a dramatic example that said that all those cues that are available during development aren't gone. Some of them can be used even in an adult brain. So I think maybe you're being a little pessimistic about all those cues being missing in the adult brain.
Dr. Vanderpoint, just for our edification, can you just explain what stem cells are doing? What in fact are they doing?
So I guess the biggest thing is that during development, they're building the brain. So the stem cell, I would say the first brain cell on the developing embryo is a brain stem cell because it builds the brain initially. And then what happens to those brain stem cells is they mostly go quiescent. There's very few of them that are active in the adult brain. There's this low level of proliferation. New neurons are always made in the hippocampus. There's some new neurons made perhaps in the olfactory bulb. There are places where they're still active, but most of them are quiescent. But they're not gone. And that was one of the great studies that was shown by Sam Weiss's lab at the University of Calgary, is that those stem cells that made the brain in the embryo are still present. They're just quiescent. And so one of the goals of stem cell biology is to activate those stem cells and get them to remake the neurons and the glial cells that are missing in various types of diseases.
Dr. Mailer?
So for example, if you happen to be a bird and there's damage to your hair cells, it'll regenerate. If you're lucky enough to be a frog or a fish, it's the same. Us poor mammals are the only ones that cannot regenerate the hair cells in our cochlea and recover from deafness. And so there's a tremendous push to say, what's going on? And the idea is exactly that there are quiescent stem cells, they're being suppressed. It turns out to be very, very tough to figure out the suppression mechanism. We have to learn about that, and that's only cochlea. It's going to be much worse in our cortex. Not impossible, just very, very hard.
Dr. Stanford, you want to?
I think I forgot what I was going to originally say, but I just want to remind everyone that Gordie Howe is improving, and it has nothing to do with the cells that were injected. If there were cells injected into his brain, I suspect it was saline injected into his brain because that would be fairly, they want to make sure that they don't put the patient back onto the airplane and they'll die on the plane.
Did you say saline?
Saline, yes, saline. So just water. It's actually with a little bit of salts in it. So, but that's what I suspect. But but he is getting better, and stroke patients often get better with exercise, with going to an occupational therapist, and that's because our brains have this wonderful plasticity in them. They can adapt and change, and there's a rewire and reconnect themselves. So there is quite a lot of capacity. There's a tremendous capacity within our brains, and we need to help them. That's why the patient goes to occupational therapy. So again, what do we do? We already have stem cells in our brain. We just need to figure out how do we help those cells to do what they're supposed to do. And that's what a lot of the work has been done, is going on right now. And just like the clinical trial that Frida Miller is performing, that Dr. Vandergoy mentioned, that this is essentially to help to give the chemical cues to those stem cells to do what they're capable of. And that's, that's a great place to start. And one of the other things is that the integrative part for my Canada Research Chair is called systems biology. And as a systems biologist, what I try to do is I try to understand what a cell fate decision, why a cell will become a neuron versus a glia in the brain. And what we do is we develop mathematical models that actually predict this. And in the field of neural networking, there's a lot of really smart people figuring this out. And they're working on making the blueprint. And that's the kind of work that Dr. Mailer is talking about, making that blueprint. But actually, it's going pretty well. And so I think there's more work to be done, obviously. But I think combine that systems biology approach with the fact that you have stem cells already in the brain, and the plasticity that occurs in the brain, and the ability to rewire and make new connections. I think the trifecta is what we need to be able to push this through to clinical trials for stroke, for example.
I want to invite you, thank you for that. I want to invite you, our audience, to pose questions, or if you have any comments, please do come to the microphone. Dr. Parker.
Sorry, I'm going to do the first question. I apologize, but I urge all of you to come up here. Don't be shy. Okay. So I have to say something about Parkinson's, because it's been mentioned out there incredibly a lot of times. So I am a Parkinson's researcher, so I know a few things, and I'm going to lay it out loud for you. It'll be controversial. So number one, fetal grafts that Bill Stafford talked about do not work. Absolutely not. So, what's the history of this? Neurosurgeons got the fetal grafts, as Bill described, put them in the patients, and did these before and after, like weight loss, before and after pictures. Oh my God, it's working. And that's the problem whenever you do individual anecdotal studies. Right? You see what you want to see. So when they did the proper trial, they spent millions and millions of dollars because they were worried about this. They did the proper trial of fetal grafts, put it into the Parkinson's patients, or didn't, and all of them received holes in the head. They didn't know. Guess what? Absolutely nothing. They didn't believe it, so they did it twice. Spent more millions of dollars. Absolutely nothing. Right? Second point. Right? And that's with one type of neuron. Right? And so the idea also that you can actually just take an aging adult, take a cell that has been degenerated, put it back, and hopefully, the Lincoln circuit. Well, guess what? That circuit, that simple circuit, and it's relatively simple compared to all the other things that Glenn Mailer was talking about, is completely different because of this plastic nature, this circuit now is completely different than what it was normally. So you put something onto something that is completely different, you're going to get abnormal results, which is absolutely what you got in Parkinson's. And that is shut down that avenue of research. Now people are going to spend an inordinate amount of time trying to figure out all these basic questions that are going to take decades, not years, to figure out if they can actually use stem cells. Because don't forget, they actually put in stuff that they thought were the actual neurons. You didn't have to turn them into anything, they were the actual neurons. With stem cells, you have to take them, make them into neurons. What kind of neurons, how many neurons, another additional step. It's more difficult. And so, secondly, I do want to make the point that there are studies that are going on for regeneration. You can see that I'm taking the opposite point of view. That actually are trying to figure out how to mobilize and incorporate the endogenous stem cells, right? So this is the study that Derek may have talked about. But it's a drug that you put in that does a whole lot of things in the body. And how do you actually ascertain that it's very, very specific for what you think is going on? Well, that's a difficult problem too. So at least for Parkinson's, I think it's going to be a whole lot more difficult than what was presented here. Not impossible, but decades, not years.
So thank you, Dr. Park. Dr. Vandekoy, it seems that Dr. Park has thrown down the gauntlet, saying that stem cell therapy has not worked for Parkinson's patients. And I believe the Michael J. Fox Foundation, which had invested millions of dollars in stem cell research, withdrew some of that funding because they noticed that the progress was not being made. So how do you respond to that?
I would like to give a different interpretation of both of David's points. So the Parkinson's trial that failed, this was not a stem cell trial, this was a transplant of fetal dopamine neurons into the brains of Parkinson's patients. And to say that it was nothing, there was no effect, is not true. What happened is you actually got too much effect in some of the patients. So the patients had dystrophic movements. So these are Parkinson's patients who couldn't move. Some of them got abnormal movements, and one interpretation of those abnormal movements was that there was too much function of the dopamine neurons, and you were actually getting dysmorphic movements. So it's dysmorphic, meaning not correct movements, but you were getting movements, right? So I would actually suggest that that trial isn't a failure. We may have had the dose wrong, but I don't think it was a failure. Now, the second point you made was with a drug trial, metformin. And I think one of the powers of drug trials is that you can actually do tests in the experimental animals. And so the test that's been done with metformin is to ask, if we remove the stem cells from the animal, do you then prevent the metformin from having its beneficial effects? And the answer is yes. So I think that's pretty good evidence that the metformin isn't working through some crazy other way. It actually depends on the stem cells for its beneficial actions.
So I suppose you joined their side.
Okay, but can I just respond to those two things? Two points. One is, I was at the meeting where they actually discussed the clinical trials on the cell replacement, right? And I completely agree with you, Derek, but that was mentioned by Bill, so I had to say it, right? So that was field graphs, actual neurons being put in. So number one, so there was this huge argument of, was it really effective, was it not effective? And what somebody on the panel said was, if I take the trial and then relook at all the data retrospectively, I can parse out exactly what the results should be, right? Which is absolutely contravenes what a clinical trial should be. In a clinical trial, you figure out exactly what you are testing, and then you test it. You don't go back and try and figure out, okay, how do I make this test clinical trial positive, right? And in fact, at that meeting, there were shouting matches about that issue. And secondly, my point to the animal model is, I've cured Parkinson's and stroke a dozen times, so thank you.
Ma'am.
So I have no science background at all, but I have a lot of life background with various illnesses of the brain, including Parkinson's. This is kind of a shout out in part to my mother. She had early onset Parkinson's, and she was the first fetal transplant patient in Canada. She was part of those trials. And I think we have to remember that the potential of stem cells is so high that it's worth a lot of investment of time and energy, in my view, as a Canadian. And it's a little bit like risk analysis. If there's high risk and high cost, well, that's a really bad scenario. But if you've got the opposite, maybe it's a good scenario. And I think stem cells are one of the good scenarios. And I think when I listen to all of the scientists here, there's a lot on which you're in violent agreement. And the disagreement seems to be in two areas. One is what's the time frame, and the other is just how complex are various parts of the brain and various brain issues. But that's how science works. To me, as a person who observes from the outside, you build from the simpler to the more complex. And so I guess as an individual, what I would say is that it's worth it. It's really worth it doing this, in continuing this. And if it's decades, so be it. But what if you cured Alzheimer's? And what if you cured Parkinson's? That'd be pretty cool.
Thank you.
Dr. Willis, perhaps we can hear from you as our neuroethicist. Can the risk ever be too great when it comes to this kind of therapy? I'm looking at the potential for stem cell therapy. Is it too big of a risk to you?
That's a very interesting question. I think I would say no. The risk of pursuing this science is absolutely trumped by the potential benefits that I think we're going to realize in the decade to come.
So what is your concern then as a neuroethicist?
My concern is of readiness today, which is what we were charged in debating. Are we ready today? In some cases, yes, but not in the context of the charge we were given today.
So what are some of the other questions then that we need to be asking ourselves that perhaps we're not asking when it comes to this question?
So, and I was making some notes for my summary remarks, but I will make them now. Come up with something else when I have to summarize at the end. I think we have to think about things like autonomy and the right to make choices for ourselves. We as a democracy, as a wonderful Canadian society, should have those rights. We have to balance those against promises that cannot be fulfilled at present, like people going abroad, and then coming back, possibly believing that they have a benefit, maybe experiencing some benefit, but in some cases, perhaps more than not, actually coming back worse than they were before. And then our society, our communities, our families, our healthcare systems have to absorb the harm that's been imparted onto those individuals who, in all good faith, went abroad in pursuit of hope and benefit. And I think that is a huge risk that we experience. So it's not mitigating what's going on in the scientific arena. It's mitigating what's going on in a sphere over which we have considerably less control. I think we have to be outspoken citizens and in supporting affected individuals and making the very best choices. I think we have to stand up as professionals and professional society, sometimes in the face of lawsuits, and hold our own and say, no, that really is not okay. And we definitely are seeing some of those therapeutic experiments in people that are not okay. They are experiments, and we don't do experiments in people anymore where they don't know what they're getting. It's actually abuse, if not torture in some cases.
Thank you. Matt?
Hi, I'm a clinician in Ottawa who has an interest in regenerative medicine. And I myself have been using PRP in dermatology to regenerate photoaging concerns, also scars, and something else I'll talk about maybe. But I attended a symposium in Florida just this February. It was a first multidisciplinary forum course put on by some of the people in Florida who have labs. They're FDA approved for tissue culture and treatment with stem cells. And we actually had a virtual tour of the Tijuana facility, which is state-of-the-art. I understand that what he had was, and it was a gentleman who had provided the therapy, he had his autologous stem cells. I don't remember whether it was mesenchymal or fat, but he had his own stem cells mixed with PRP injected intrathecally. So I don't think it's snake oil. I think the reason why people have to go to Tijuana and places like that, there's a place in the Bahamas, there's another one, I think it is another small island, is because of FDA legislation. And the FDA cannot legislate the practice of medicine, though. And so people are allowed to come to the facility in Florida. They can have their own stem cells extracted, mixed together with PRP. They can inject them into, basically, they have orthopedic guys doing, and actually in Ottawa we have orthopedic physicians who are doing PRP therapy for all our athletes. They used to go to Europe. Now they can have it done here. And I don't know if they use stem cells as well. I'm not sure about that. But they cannot practice our legislative practice of medicine. So these people can have their own stem cells removed, usually through lipo harvesting, and spun down, mixed with PRP, and they can have them injected that same day, providing the cells are not manipulated. If you have a really sick patient and you harvest their fat cells and you want to extend the cell line, then they have to go to another lab and that's tissue, and that's where FDA has a problem, and they cannot inject it back into the patient. So they go to Tier 1 and they have their injections. So, I mean, to me, the listening to all these specialists that were there and giving their anecdotal reports, but I think it's unethical to do a randomized clinical study on a very sick patient, using their own skin cells, their own cells to regenerate. That's all they're trying to do, using their own stem cells to regenerate their own problems. I think it's unethical to randomize that study and give them maybe something else. These are sick people, and yes, that's all we have right now, but some of the anecdotal reports are quite remarkable. I think you have to keep an open mind. Sometimes a research it's like you can't see the forest for the trees. Well, here I think you can see sometimes the benefits, and no one had any problems with safety, and sometimes you have to kind of be an innovator, I think, as a clinician. There are some of us who will be the first to try something. There's some of us who will wait till it's proven, and there's some of us who probably never do it. So I just like to make that point.
Thank you.
Thank you.
We have a little bit 7 minutes before we have to wrap up. And so what I'm going to try and do is I'm going to try and squeeze as many questions and comments, and we'll have a truncated closing remarks segment. Okay, so I'm just going to ask, please go ahead.
Hi, I'm not so experienced in life-boring science, but this is more a question of, it's not directed to any side of the argument, it's more a question of how. I learned that when someone has a stroke, the brain has the ability to rewire itself so that other sections that weren't affected can take over some of the functions that other parts of the brain that were affected would usually do. And I saw that in my dad because he had a stroke. So I was wondering, if you use stem cells, would it take over this process, or would it regenerate the parts of the brain that were affected by the stroke?
I think there's not enough evidence out there to decide that question. I think that the goal, I think, of most stem cell biology is to rebuild the missing part of the tissue. But there's also another whole field that says that stem cells don't have to rebuild the missing tissue. They have to just stimulate the other cells that are there to do a better job. And so many of the effects of stem cells may not be direct effects from stem cells rebuilding the tissue, but releasing something that causes the other cells that are there to change their function.
So it's like a catalyst.
Yeah, and so I think there's not enough evidence in the brain to decide between those possibilities right now.
Sir?
Yes, as members of the public who are interested in matters like this, we tend to get our information from the media, which may or may not be accurate information, and I commend Dr. Park and his team for having this week of fascinating lectures and discussions.
CBC is always accurate.
It's been a treat this week to get information directly from the source and to have some stimulating discussions on some fascinating topics. I'd like to address the lady who had the question of risk versus cost and say that I'm sure I'm not the only one. I'm now 80, diagnosed with early-stage Parkinson's. I've had a good life, a full life, and if there was a risk to undertake some treatment or therapy that might prove something, I'd be very happy to volunteer. And I'm sure there are a lot like me who would do the same. So that's part of the risk equation. You need people who will volunteer to accept the risk and help to move the science forward. The last point I'd like to make is we understand that there's considerable work in stem cell application in Britain, and I wonder what the panelists think of the work that's being done in Britain. Are they further advanced than we are in Canada? Do they take different risks? Are they making good progress with their work?
I would say that there's great stem cell scientists strewn around the world, and including in the UK. And the UK got a lot of funding in stem cell research, which really propelled things certainly forward. And I think bringing back your point about being willing to take the risk, that should only be done in the case of a clinical trial, because that's the perfect thing for you to do. And just like cancer, all cancer therapies are basically done with patients who don't have a choice. And so if it's in a clinical trial, then we'll learn something, even if it works or even if it doesn't work. And that's the difference between that and going to Tijuana, because the cells that were injected in those patients are fat stem cells, and fat stem cells can't become neurons.
Dr. Miller.
So bringing up the UK reminds me of an old friend and colleague, Jeffrey Reisman, used to be at Mill Hill MRC Institute, and he noticed something interesting. You have a cold, and you sneeze, your nose is running. The receptors for smell, they're being sloughed off, they die. You recover, and you can smell roses or whatever perfectly well. There are stem cells in the nose, olfactory receptor cells. They regenerate olfactory receptors. Their output penetrates a little bone and makes the right connections. Now, Jeffrey Reisman noted this. He said, wow, stem cell neurogenesis, making the right connections, this is perfect. How does this happen? And he had an idea that certain very special cells did the guiding. So, excellent scientist, what does he do next? He takes those guiding cells that work so well for the sense of smell and puts them into a damaged spinal cord. And he says the rat is recovering. It never worked out though. It could not be replicated on a routine basis. So, what works for the nose doesn't work for the spinal cord, basically. So there's my little message from the UK from about 10 years ago.
Okay, we have 5 minutes to go. I'm making the executive decision. We have 5 minutes left before we wrap up. So very, very quickly, and we'll have the closing remarks.
During the course of the debate, you've addressed primarily adult conditions, and you spoke to the effect of strokes in the brain that is no longer developing. So what about, where are we at in terms of stem cell and regenerative therapy for the developing brain, pediatric strokes or cerebral palsy or congenital neurological conditions? So maybe you could address where you would think we would be in terms of a brain that's still developing. Thank you.
So I think you're absolutely right. In the developing brain, there's good evidence in animal models that the developing brain can handle injury better. So the same sort of injury in the cortex in a very young rodent shows much greater recovery than that same or similar lesion in an adult animal. So because one interpretation is that because the stem cells are still active in the developing brain, then they're already active and they have the ability to recover better than a stem cell that's quiescent in the adult brain and not dividing. So I think there's good evidence in animal models. I think the evidence in humans is just not there yet.
Final question.
Hi. This is more of a science question than an actual debate question, but I know you mentioned the issue with the scaffolds and all these signs that guide these neurons to the right places in the developing brain. But I noticed that you also mentioned that neurons are also constantly being created in the hippocampus, and I was wondering how you said that they know where to go and they know which part of the brain to address and how. I mean, like that's kind of there are no guiding signs, and how do these neurons know where to go and why can't we sort of do that?
One specific set of neurons that keep developing the brain, and that hippocampus, they seem to retain the guideposts. It's intriguing, just like the ones in the nose that know how to get those in one particular part, go to the one part of the hippocampus, they somehow retain the ability to have new cells forming, and they know where to go and they know what to become. Why just that one part of the brain? It's a clue, but we don't know a clue to what just yet.
Dr. Vanderbrink, you seem to want to respond. Okay, great. Well, I think what I'm going to ask now is that if each of our panelists could give a closing remarks, 1 minute in length. So I think what we're going to do is we're going to begin with Dr. Naylor.
So I've had this discussion with my garage mechanic, why do this research? And what I tell him is, you can have uncertainty or certainty. If you continue to do research on stem cells and brain regeneration, you don't know if you're going to be successful. You don't know if you're going to be successful. It takes years, decades. You just don't know. You're uncertain. If you don't do the research, you're certain that you're never going to get a cure for any of these diseases. So I would choose uncertainty.
Thank you. Dr. Vanderkoy.
I think I'll just claim victory because Len and G are clearly on our side, and so I'll just leave it at that.
Dr. Ellis.
Well, I'm going to conclude with two main messages. One is know what you're getting. So I will share a very quick story with you. I have two beautiful dogs who I absolutely adore. One is a puppy who loves to swim in a river, and he got an ear infection. So I took him, and I happened to have my 12-year-old beautiful husky with me as well. With no general remarks about British Columbia veterinarians, she treated my puppy for his ear infection and offered me stem cell therapy for the little bit of arthritis that my husky had in her thumb. And I was like, why would I want stem cell therapy for that? So know what you're getting. And my second message is one of informed hope. And that is, you may participate in a clinical trial, and of course we embrace your willingness and your altruism to come and be part of our research. That is what will make this go. You may decide to go abroad, and you may enjoy some benefits. And Some of those benefits may well be a placebo effect. And, we used to think about placebo effects in a very disparaging sort of way. We always used to think, oh, so it's this mind thing playing tricks with you. But in fact, placebo effect is very beneficial and very positive. If you feel better, even for a short amount of time, that may well be beneficial. But be informed about what you're choosing, what you're going for, what the real promise is, and what might be underlying your hope and ultimately the decisions you make and the benefits you gain from them.
Thank you very much. And Dr. Stanford.
So I want to echo all my colleagues here. And I just want to, just to say that in my Stem Cells 101 presentation, I just talked about the stem cells that were relevant to the brain. All of our tissues have some stem cell activity. In fact, our red blood cells, they live for only 4 months. So without blood stem cells, we would all be dead within a very short period of time. But blood stem cells cannot become neurons, nor can fat stem cells or MSCs or mesenchymal stem cells. They can become the cells within their own tissue. So beware if you're looking into clinical trials or looking into going elsewhere outside of our borders, then know what stem cells you're getting and what they can do.
Well, at this point, I'd like to thank our panelists. I'd like to thank Dr. Mailer, Dr. Hillis, Dr. Stanford, and also Dr. Van der Kooi. And I'd like to thank them as well for enduring my at times unconventional and cheeky moderation. And I'd like to thank our audience as well. And we look forward to seeing you again next year. So thank you. Do stay for the reception. And I'm going to ask Dr. Park to come forward right now just to end the evening. Thank you all very much.
Thank you very much, and really an amazing job by the panelists. Can we give them a round of applause? I apologize for taking up a little time over there. So when you go back and have a little food, you can please talk to the panelists and really get their opinion. Maybe in a little bit more private form if you were a little shy. I tried to get there was no fists. I tried to get it up and going. It didn't really work. Anyway, so thank you all very much. Do we have where's my audio? Do we have the video? Yes. Okay, I just wanted to, many of you have seen this many, many times, but we really are all about you, the patient and the community. We made a video to try and promote the mind and to really reflect this concept that patients, people in the community are very extremely important. We have a view that they are the center, they are strong, and that we need to work as quickly as possible to make a difference. So, thank you very much, and we'll end with a video.
Our patients are strong. Every day they live with neurological disorders such as Parkinson's disease, stroke, depression, and ALS. And every day they fight to maintain their quality of life.
But they can't stay strong forever. Seulement une recherche novatrice, ainsi que des soins cliniques à la fine pointe de la technologie, peuvent les aider. We are here to make it happen. Par une meilleure compréhension de la complexité du cerveau, nous pourrons découvrir son aptitude à s'adapter, à changer et à guérir.
Together we will reduce suicide by 20% by the year 2020.
Personalize Parkinson's care
and eliminate the effects of stroke.
Just before we leave, I know that Dr. Vanderkoy declared victory, but you, the audience, should really determine that. And so I'm just going to ask, by show of hands, if you believe that stem cells are ready for regenerative therapy. If you could just raise your hand. Okay. And if you believe that stem cells are not ready for regenerative, wow. I think it's almost 50-50. 60. Anyway, thank you all very much. Thank you.